You can see your screen, and for a minute, you can go ahead.
Okay. Hello, everyone. I am Mahbubur Rahman. I'm an assistant professor and I am working at the North American University at present. It's in Stafford, Texas. Today I'm going to present an interesting topic. The title is a novel index-based multidimensional data organization model that enhances the predictability of the machine learning algorithms. Actually, in this research, I introduced a data organization model that can be used in the supervised and unsupervised learning algorithm, and it can also enhance the learning outcome. So this is the overall presentation topic for today for myself. This is the overview. First of all, I will explain the motivation behind this research. Then I will provide some background in this field, what is going on. Next, I will explain the data organization model. Then I will explain supervised learning by the data organization model. Then unsupervised learning by this data organization model. Then results, and finally conclusion. So let's get started with the motivation first. The motivation comes from the fact that learning from the multidimensional data is challenging because of the curse of dimensionality. As the dimension increases, so does the increase the complexity of learning. So what can be a solution? What can we propose? So in this research, we proposed a solution, and it is an ordered index-based data organization model. And this ordering maps the multi-dimensional data set into a reduced dimensional space. It also ensures that the information associated with the learning can be retrieved back and forth efficiently after mapping. Otherwise, the information might be lost and the learning can be hampered. So this is the motivation of this research. Next, I will explain some of the background. There are several high-dimensional data organization models based on indexing, such as SR3, R3, KD3. These are tree-based data organization models that follow the complexity of tree while inserting, deleting multidimensional data. One of the recent patents from the Google has explained the methods of searching a multidimensional dataset by mapping the data to the nodes in the multidimensional hyperspace. So this is a mapping to the multidimensional hyperspace. However, this searching in this multidimensional hyperspace can be complex and computing intensive as well. As a result, we have introduced this data organizational model in a reduced dimension that has efficient data access, manipulation schema, along with the stored information that can be used in the learning outcome of the machine learning algorithms. So this is the motivation and background of this research. Now I'm going to deep dive into the data organization model and how it can impact the supervised and unsupervised learning. So first, the data organization model. The data organizational model is a two-dimensional map of the original multidimensional data set. This data organization model is ordered on the Euclidean norm and stores the original index position along with the Euclidean norm of the data sets. Let's have a look some of the organization of these two data sets. So first one is the original n-dimensional data sets. That's just a conceptual view. So the first column here is the index, and the rest of the columns represent the dimensional values of multidimensional data. And from there, this ordered index-based database can be formed, and it has original index and Euclidean norm formed as a tuple that can be used back and forth for different types of analysis that I'm going to explain later in this presentation. Let's see some of the features of this data organization model. One of the features can be operations in this data organization model. We can map the original multidimensional data from the ordered database by constant time, since it keeps the original index position. Also, any search by the Euclidean norm can be done by logarithmic scale. So this type of enhanced database operation can be included, can be provided by this ordered index-based database. Another feature is the information reuse in this text table. I actually provided in detail explanation. Also in the paper I explained. I just to provide here, I just want to provide some highlights. So Euclidean norm, we know it has this form of equation that is that is given in one. Then Euclidean distance between two multidimensional vectors has this formula, that is formula number 2, and this Euclidean distance can be expanded using x minus y whole square formula. And the interesting thing is that in the equation 4, we see that we already know the Euclidean norm of both these two multidimensional points from the order database, and the rest unknown is just the dot product of these two multidimensional vector. So this way, this organized database can provide such information that can be reused in the machine learning algorithms, and it can enhance the overall learning and computation. Additionally, cosine formula, I mean this Euclidean norm can be used in the cosine formula as well, that is given in formula number 5. Another interesting feature of this data organization model is that it can provide a searching space for a point of interest. In figure 3, we see that this figure represents index versus Euclidean norm of the ordered database. So if we plot this index and Euclidean norm from the ordered index based database, we can see some of the similar concepts. I mean, we can then search for a nearest neighbor that exists in the circle having the radius of the minimum distance of its immediate neighbor. Actually, I will explain more thoroughly next slide. So this is just a conceptual figure. So this is the overall benefit of using this type of data organization model. Another concept of okay, so in this slide I will explain the nearest neighbor search algorithm using this ordered index based database. So in the left section I have explained how we can find a nearest neighbor for a point of interest. The two immediate neighbors are one index up and down, that is left and right of z respectively in the figure, from the index position of the data of interest in the ordered database. So these two immediate neighbor resides one index up and one index down of Z in the ordered index based database. And then next, the minimum Euclidean distance between these two immediate neighbors provides the searching space for the nearest neighbors of the data set of interest. So next, in this algorithm one, I have explained how to calculate the searching space for a point of interest of a searching space of nearest neighbor for a point of interest. So um, this is the overall benefit of this data organization model. It can provide the searching space to find the nearest neighbor, information reuse by the Euclidean norm, and finally easy and direct access to the main data source. So far, I have explained this data organization model. Now, how can this data model help in the learning outcome of the supervised and unsupervised algorithms? So in the next slides, I'm going to explain them. Supervised learning by the data organization model. The supervised learning model requires the label data sets for learning and predicting the outcome. One example can be k nearest neighbor. In k nearest neighbor algorithm, we know that the neighbors for a new point of interest in the data set are the k closest instances. And then to locate such k nearest neighbors, the algorithm must first calculate the Euclidean distance between each record of the dataset and the point of interest, and finally it must order them to find the k required instances. So here we have seen that for each of the new point of interest, it needs to order these data sets, also calculate Euclidean distance. So there are repetitive calculation processing going on. So in this data organization model, we can see that this data organization model can provide such information for identifying k nearest neighbors for a point of interest. As in the previous slides, I have explained that this data organization model can provide the searching space for the k nearest neighbors of a point of interest. So here in this diagram, you can see previously this Z and for this point, if we can search inside this circle, we can find the nearest neighbors for this point. And then this searching space can be increased to search for more nearest neighbors. Definitely we can increase this. And finally, the ordered database, this ordered database can be reused again to find the k nearest neighbors for a new point of interest that is say a point that is indicated as B in this diagram. So in this way, this data organization model can help in this supervised learning algorithm. Let's see how it can help in this unsupervised learning. The unsupervised learning algorithm does not require the label data sets. One example is k-means clustering. The existing k-means clustering algorithms calculate the Euclidean distance among the centroids of the clusters and the points until the convergence of error. And as a result, the overall computation involved here are repetitive and expensive. So here, same as previous KNNs, we find that k-means there are repetitive and expensive operations are going on. So let's see how unsupervised learning can be enhanced by this data organization model. Actually, the ordered database can provide the maximal number of clusters by selecting the mid-index point Actually, in this figure, we can see that it is X, and then determining its searching space. So we know from the previous slide that this data organization model can provide the searching space for a given point, and for this k-means clustering algorithm, we can start from the mid index point of this order database, and then we can move above and below the searching space of the mid index point, and for each of these point that we find above and below the searching space of this mid index point, we can calculate its cluster, its nearest neighbors, that is represented in the figure as cluster 2, cluster 3. So in this way, the maximal number of clusters can be reduced to the optimal number of clusters by applying agglomerative divisive hierarchical clustering algorithms. In the figure, I have explained with the dotted circle that using agglomerative clustering, these um, one, two, or many clusters can be combined, and as a result, we can find optimal number of clusters. So this data organization model actually can provide maximal number of clusters initially just by organizing these multidimensional points. Next, I'm going to explain the results. Results have been analyzed by execution time, performance comparison of using the data organization model. So what do we mean by execution time? The data organization model follows the steps below to be formed, like calculation of the Euclidean norm of each data set. Next, organizing the data on the order of the Euclidean norm, storing as a pair of original index position and Euclidean norm into a hash table or dictionary. So these three steps combine the overall execution time required for the organization of the data model. Next, I will show how much time it might take while varying number of dimensions and fixing the data size. So this is the overall execution time in second, and here we have fixed the data size in 1 million. However, we have increased the number of dimensions, and we see linear increase. Next, we have fixed the dimensions. However, we have increased the data size from 1 million to 3 million, and we find linear increase, linear increment of overall execution time for this data organization model. One comment I would like to make that this execution time can be further improved by using high performance computing environment like CUDA graphics processor. That's one enhancement of execution time available for this organization model. Now, from results perspective, the model performance with and without the data organization model, the KNN with the data organization model shows constant accuracy over the number of nearest neighbors. So we have compared the K nearest neighbor with the data organization model and without the data organization model, and here is the outcome. For execution time, we have seen that since this KNN with the data organization model requires some little extra time for finding the nearest neighbor, and also K nearest neighbor on top of that. So That's a comparison of execution time of KNN using data organization model and just plain KNN. Next, k-means results. So we find very interesting result for k-means here. So in the elbow method, actually we try to understand the number of clusters required for a particular data set. So the k-means with the data organization model provides 8 number of clusters, and the k-means from scikit-learn package provides 4 number of clusters for the iris dataset, and actually these 8 clusters can be combined to 4 number of clusters by providing agglomerative clustering technique that I explained in the previous slides. So in this way, this data organization model can help to predict the optimal number of clusters initially just by the organization of the data. So that's all about for today's presentation. Conclusion, the analysis of the multidimensional data increases as the number of dimension increases. We have explained that this complexity of analysis can be reduced by organizing the dataset in a reduced space. And our approach is simple, easy to understand, and can be integrated with the existing machine learning algorithms. This is the future work. So also this data model can be integrated in the cloud to further understand the similarity clustering tendency of the multidimensional data. Also, it can be used as a searching engine for the multidimensional data. Acknowledgement goes to the Department of Computer Science, North American University. Also, I would like to thank organizing committee members of 6th International Conference on Data Mining. Thank you very much. These are the references, and thank you, everyone. Any question or comment?